Solving linear inequalities in two variables. When dealing with linear equations with two variables, we explained that a single linear equation gives an infinity of number pairs that are all solutions for the given equation. We cannot expect anything else when dealing with linear inequalities, as they usually contain more possible solutions than the corresponding equations. In other words, the number of possible solutions of the linear inequality, we have the following shown on screen, is much greater than that of the corresponding equation. We have the following shown on screen. Despite both having an infinite number of possible solutions. Linear inequalities with two variables are better understood when using the graph method, which we will explain in tutorial 10.3. However, we can use analytical methods to solve linear inequalities as well. Just one thing to remember, we have to choose a range of allowed values for the dependent variable x, and based on this range calculate the corresponding range of values for the dependent variable y. For example, if we have to find the solution set of the linear inequality, we have the following shown on screen. If the variable x takes the values from the segment 2, 7, we must solve two linear inequalities with one variable like those discussed in the previous lessons, where the variable x is replaced by the two limit values of the given segment. In this way, the two linear inequalities are solved only for y. Thus, for x equals 2, we have the following shown on screen. And for x equals 7, we have the following shown on screen. Thus, since the values of y must be limited between the values found for the two limit values of x, we obtain for the solution set of the inequality the values of y that extend from 5 and up for the minimum value of x, to 20 and up for the maximum value of x, without including these limit values. We can check whether a certain number pair belongs to the solution set of a linear inequality, or not by substituting the values in the inequality. In this way, after doing all operations, we see whether the final version of the simplified inequality is true or not. Let's take an example to clarify this point. Example. Check whether the number pairs 3, 1, -3, 4, and 0, 2 belong to the solution set of the inequality. We have the following shown on screen. Solution. First, let's write the inequality in such a way as to isolate y on the left side and express all the rest of the terms on the right side of the inequality symbol. Thus, we have the following as shown on screen. Looking at this inequality from right to left yields, we have the following as shown on screen. Applying the properties of inequalities yields, we have the following as shown on screen. Now, let's check whether the given number pairs are solutions for the previous inequality or not. Thus, for the number pair 3, 1, x equals 3 and y equals 1, we have the following as shown on screen. Hence, the number pair 3, 1 is not a solution for the given linear inequality. As for the number pair -3, 4, x equals -3 and y equals 4, we have the following as shown on screen. Hence, the number pair -3, 4 is a solution for the given linear inequality. Last, for the number pair 0, 2, x equals 0 and y equals 2, we have the following as shown on screen. Hence, the number pair 0, -4 is not a solution for the given linear inequality. That is all for lesson 10.1.6, and the end of tutorial 10.1. To continue this chapter, please watch 10.2, Introduction to Quadratic Inequalities. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.